All right. Um, so since we do all of our submissions by, or almost all of our submissions by email, what I found is that my email program sometimes can be rather brain dead, and given the state of technology in this campus, slow, because for a university internet connection, it's not what it should be. At downloading high-resolution pictures, like the four you just sent me, Jesse, that I swear it spent like a better part of an hour just trying to pull them down on my computer, and I think it kept going back and trying to do them again. I don't know why. So that's why I just barely managed to answer your questions before class time. So if chances are like that kind of resolution results in like a 3 megabyte file per picture, and it's probably far more than enough resolution than is necessary for me to be able to read it. So because it comes in really, really clear. So so if it's convenient, it might be better to either use a low resolution. Like for instance, when I send pictures to my phone, it asks me about what file size to choose, and sometimes I choose a smaller size. Or I know some of you do homework is if you're sending several pictures, like for instance pictures of your work on paper, and you put them all in a PDF or a Word document, and you send that. That works really well because then it's just downloading one file. Things that move a process along of either grading or answering questions a little more efficiently. Okay. All right. So to this point, out of the 21 of you in the class, I'm only aware of one who is doing a take-home. Maybe others aren't, just haven't asked any questions. I don't know. Well, regardless of how many or how few do it, a deal's a deal. But in case it makes a difference, I've pushed the due date back by a day, so you have until the end of the week. For whatever you're working on, whether it's that or the or homework 3 that's going on, I had a number of questions in the last couple days, so be sure to check that at least once a day, in case the problem you're working on there's something in there that can help you. So these are important habits to get into, if not already. Okay, now speaking questions, does anyone have any about either item, homework 3 or the take home?
I have a general question.
Okay.
So do we get the privilege of starting the finals before like we did in differential equations?
Oh, that. I didn't make room in a schedule for it. Okay. All right. So for those of you who don't know, what he's referring to when I taught 285 last semester is for all of the tests that were in-class tests in the final, I'd have you guys start them during a class period, and then you would turn them into me. I would not grade them, but mark where you went wrong, or leave it, or tell you that you did it right. So you'd have some feedback, give it back to you to finish. Now for a final, what I had to do was do that during the last day of class, and then during the regular final exam time, you would have a marked up version. I'm not opposed to that. This is a matter of practicality. So let's take a look at the schedule. And okay, so then how that would have to work. Okay, because what's happening? Shut up, Sor. What's happening since we're at 3 locations? So I know at Gulf Park, Ms. Marlene is going to be proctoring during a time slot, so I'd have to get her those tests, but I think that could be done. And then, Caraday, I'll just see how this is going to work for you. Taking, okay, well, I'll have to ask about, figure out what to do about that for the purpose of a final. Same situation. Okay. What?
I plan on being up there the day of the final, but are you talking about like the class period before the final?
Right. Yeah. Well, that's what I want to take a look at now, is looking at schedule. Okay, because here's what's being covered starting from today, all the stuff on integration. And okay, so the last day of class is here, November 30th. And so what I have scheduled for that is a review. Okay, because I am going to put a practice test out. I just need to put everything together for that. So, all right. Here's what I can easily do. Is on that last day of class, we'll have 75 minutes, and so I can use part of the time just for review. Also, we have time during class every day for questions anyway, so we could use some snippets of class time before November 30th if you have questions about the practice exam, so we can talk about those things. But so I'll break up the 75 minutes on November 30th to be part last minute review, and then other part to actually get started. And then so what I would suggest in that case is I can't say yet how many problems there will be, but at least try to start as many as you can, because if you feel like you know what you're doing on it, go ahead and leave it and start another one. Because then when I look at them, I can tell you on each problem, oh, you're going the wrong way, or no, you're not. If you don't write anything down, I can't give you any info. So, okay, but I'll talk more about this when we see how many problems. I can tell you how many problems there are. But so that's what we'll do. So November 30th is review plus start of final. So Caraday, I don't know if it'd be practical for you to be up here on that day, or if not, let me know and we'll figure something out.
Okay.
So that you get the same thing. Okay. Gulf Park people. Well, I guess Ross, you're the only one here today, right?
Yeah.
Okay, but I'll tell everybody. I'll ask some faculty member down there to handle things so that they can administer you that part of it and then get them to me quickly, like scan them so I get it right away, so that everything will work. Because that's on Thursday, and then the following Tuesday, 4:15 to 6:45, is when the everybody will be taking the final. Okay. Grades have to be. I have to turn in your final grades the following Monday, which is December 11th. So I have to have at least a little time to incorporate any last submissions of like homeworks and such. I've set December 8th, which is commencement day, for the last day to submit homework for. I can give a little more leeway, but at that point, it's like we're really running out of time. So also, it'll have to be sent to me because from like December 8th onward, I'll be away. But you can I could accept email submissions, but at some point there has to be enough time to grade them before Monday at 11 a.m. is when it's all over. Okay. All right. Other questions of any kind? On anything? Such a quiet bunch you are who are getting all the problems done easily. Okay. Or seeing what kind of a buzzer beater you can do by not starting it until like the 13th for the homework. Okay. Well, at least you guys are getting all the quizzes in. So. Right.
Okay, so I figured out that it may be possible, but I'm not sure if I'm on the right track because.
Oh, the very first problem?
Yeah.
Okay.
When I looked at it, it comes up since it's repeating.
Yeah.
There's like whatever you end up putting in, that thing repeats. That
Yeah.
string repeats. So I don't know how you would write that out. I guess.
Okay.
So show that entire section repeats, not just a specific number.
Okay. All right. Let's. All right. So since this deals with this is a chapter 2 thing. What was that?
Sorry.
What? Oh, okay.
I was trying to say.
Oh, okay. Yeah. No, but that was just amusingly surreal. Okay. All right. Okay. Okay, so this is problem 1A, which, so the question is it's 8/3, right? It was like 2.6 repeating?
It's 2.6 repeating.
Yeah, can 8/3 be represented exactly in a floating point system of any positive integer base? Because we know, as we know, 8/3, anything like over 3 that doesn't divide evenly is a repeating decimal in base 10. And the question is there some other base for which we can represent it exactly? And this is kind of like one of the problems I came in homework 2. Recall that 1/10 can be represented exactly in base 10, obviously, because it's 10 to the minus 1, but not in base 2. Does anyone remember? This was exercise, it's like 643 or 644, something like that, where you had to deal with 0.1, and I recommended you use format hex to see what at least looked like in base 16, which gives you an idea of what it looks like in binary. Does anyone remember what it looked like? 0.1 when you did format hex on the homework I just graded. I'll refresh your memory. Repeating. Actually, if I go back to regular format, let's look at 2/3. It's going to give me as many 6s as it can, and then it rounds up to a 7. Same thing here. Bunch of 9s rounds up to an A. Whereas if this was chopping, it would be all 9s. If this was all chopping, it would be all 6s. It's the same kind of situation. Okay, So here's another example, 1/10 can be represented exactly in base 10, but not in base 2. Instead, repeating binary. So, so to handle this, okay, that's strange. Okay. So what do the digits in the Mantissa mean? And if we go back to the definition of floating point numbers, okay. Ah, dang it. Okay. Okay. Here, definition. What we have here are each digit is multiplied by a non-positive power of the base. So, for instance, when you see decimals, like this 2.6666 repeating, you have 2 plus 6 over 10, plus 6 over 10 squared, plus 6 over 10 cubed, etc. So it's actually not the repeating decimal that you want to focus on. Focus on the fraction, not the decimal. So that'll give you an idea as to what could work as a base. Also, recall how to get the exponent. That's the log in that base of the absolute value of your number. So if you have a base that you think might work, you can find the exponent and get that out of a picture. When you're dealing with a number that is less than 1, or so in other words, don't work with just 8/3, but the remove the integer part, because that's something that's going to be left to the left of, well, normally I would say the decimal point, but the point in whatever base you're using. So really it's 2/3. Can you how is there a base in which you can represent that? So so in binary, if it was base 2, what can be represented exactly? And the answer to that is a combination of linear combination of 1/2, 1/4, 1/8, and so on. All the well, also I should say integers plus all that. But once you set aside the integer part, it's negative powers of a base.
So if you do that, is it wrong or right to show it as a combination of, like, let's say you're going to do it in binary.
Yeah.
And you break 8/3 into 2 plus whatever in binary plus whatever in binary, where the whatevers end up becoming the 2/3 that was.
Okay, now I want to make sure that I have to emphasize one thing here. It has to be a... dang it. Stop that. Sometimes I really hate this program that I just paid $126 for. But that's okay. I paid even more for Matlab because I'm not a student. Finite linear combination. So for example, if it weren't for the finite part, I could take these negative powers of 2 and keep adding the right combination of them to get arbitrarily close to 2/3, but I would never get it. Just as I could never hope to get 1/10 either. So that's why neither, and we already know what happens in decimal, so that's why neither of those bases would work. So what happens is if we're restricting to a finite combination, this is very limiting in terms of which fractions can be represented exactly. Because what happens is you're adding these up, and you want to make them into a single fraction. What do? It's a common denominator. And what's your common denominator? In this case, it'd be a bunch of 2's multiplied together. So in binary, the only fractions I can get exactly are ones where the denominator is a power of 2.
So you have to figure out a way to do power 6 since the bottom decimal can is 2 over 3. So if you can turn 2 over 3 into a fraction where it has a common denominator of 6, you can just go ahead and break it down into numbers that would theoretically add up to 3, I guess.
Well, the thing is, here, but the point is, because binary only allows fractions that are powers of 2, that means that base should be abandoned as a candidate. So
then hexadecimal.
Well, hexadecimal, that's even worse.
Yeah.
Powers of 16. So the thing is,
Base 9 work, you think?
what?
Base 9?
Warmer.
I'm going through all the different bases.
Remember,
Base 12.
you're allowed to use any positive integer as a base. Although 1 would not 1, but because you wouldn't have any digits. But so any positive integer greater than 1 is allowed. All right. So, okay. Other questions of any kind? Alrighty. Suit yourself. Okay, because so it's next week when homework 3 needs to be in, and then after that, better get cracking on homework 4, which is on differentiation and integration. I'm going to be continuing to cover. Okay. About so one preemptive thing I'll say about homework 3. For any dang it. For any coding problems, because I've seen this from more than one person, never use 0 as an index in Matlab. Certain languages like C++ do have 0-based indexing. Matlab is not one of them. You have to index starting from 1. So if an algorithm, like in the book, uses 0 as an index, like a loop going from 0 to n, which is very common to do, you have to just shift these values by 1 when you use them as an index. Now, in a formula, you don't have to change them, but for an index, you do. You're supposed to use 1-based indexing. Also, in some of the algorithms that come up in this assignment, you have loops that are going backwards. So remember how to count backwards in Matlab. So for instance, you might have a for loop. In fact, it does come out like for I equal. If you want to start from n and go down to 0, it would be like you don't do n to 0. What do you have to put in the middle? Yeah. So that's how you would handle that case. Okay. So these are things I've just observed. One other thing, also, coding problems piggyback off each other. So call your previous functions. For example, in 623, write a function baryweights. It gives you a barycentric weights. 624, you have a function that evaluates Lagrange polynomials using the barycentric weights formula. So first thing you do, call your baryweights function. And you get the output from that, and then you just go ahead and use it. So you're not redoing that. And that's why in certain problems, the coding is very short, just because it's delegating to other functions. And that's really one of the good things about programming, is that it lets you develop these building blocks, and then you can develop large programs rather quickly by building things on top of them, knowing that those tasks will be handled correctly. Okay, so some of the problems in this assignment illustrate that. Okay. All right. Now, last time I did not get to the end of the example I was working with numerical differentiation, so I'd like to polish that off. So the task yesterday, or Tuesday, was deriving this center difference formula. So the derivative at x0 is uses values to the right and left. And then we have this error term here. And what I got through last time was how you arrive at this formula and this error term using Taylor expansion. So I won't go through all that again, obviously, but what I have done here is given a list of steps. I know you guys didn't like step-by-step procedures, so here's one. So where you first decide what is the form of your approximation. In other words, which points are you going to evaluate f at to get your derivative? Okay. Not sure why our only co-student left the room. Okay. All right. And then for each point in this form, except for f of x0 itself, Taylor expand it around x0. Then you go ahead and substitute them into this form, and that's what was done last time. Then if you group the terms together, like all the f of x0 terms together, all the f prime terms together, all the f double prime terms together, and so forth, then you want certain terms to go away, and you want certain terms to persist. For instance, you want to have f prime by itself. So the coefficient of f prime needs to be 1. All other terms, like terms multiplying f of x0 or f double prime, you want those to go away. So what that gives you is a system of linear equations for the coefficients, the c's, in this form. So you go ahead and solve that system, which you can use Matlab to help you. So then you get your coefficients, but then after you make terms the way you want them to be, like if either they go away or you have f prime by itself, the next term after that, the first non-zero term, tells you what your error is. Okay, so that's the rundown in words of what was done last time. In fact, it would be a good idea to look at that procedure and also compare it to this verbal description, so you can see what all those steps are. Without being certain, I think this would be a good candidate for a final exam problem. Well, it's already a homework problem, but also a candidate for a final exam problem. Derive a certain differentiation formula using Taylor expansion or Lagrange interpolation, either one. Okay. Now, where I left off last time, I wanted to show you the second approach, and that's using Lagrange interpolation. So a quick recap of what I'd done on Tuesday. So I'm saying that the derivative, the exact derivative, is equal to f is equal to the exact derivative of an approximate f. So P2 interpolates f at these 3 points. So it's approximating f by quadratic. And then I have some error that I want to figure out what that is. And then what I do is I write this interpolating polynomial in Lagrange form instead of Newton form like we've often done. So we have each of our f values are the coefficients, and then we're multiplying by these Lagrange polynomials. But I'm going to show you an example in the book where this sort of thing was done. Okay. All right, so here's an example where I'm deriving a different differentiation rule using Lagrange. And what happens is, here are the Lagrange polynomials. It's a bit of a mess. So instead of doing that, what I want to do is use simple, because my interpolation points are, here they were x naught plus h, x naught plus 2h. So I want to use simpler interpolation points. And that's why I do a change of variable. S is x minus x naught over h. So whatever multiple of h I'm using, this integer I here, those will be my new interpolation points. So I have this association. Here are my x values, and here are the s values that go with them, using this transformation. It's just the multiples of h, so minus 1, 0, and 1. Okay. So then I want to switch from x being my domain, my independent variable, to s. So I make these definitions. So here I have functions of s that are equal to my functions of x. And they're just related by this change of variable. So f tilde is equal to f, but using s instead of x. And then similarly, I have p2 tilde is equal to p2, but is a function of s. And I can go both ways. Here's how I go from x to s, and this is a reverse. So just a linear scaling and shifting. Okay. So p2 tilde interpolates f tilde at these simpler interpolation points, minus 1, 0, and 1. So in general, where do you get these? It's from the points that you use in your approximation. So because I'm using these points, minus h, 0, and h, those multiples of h are my s values. Okay. So now my derivative is just equal to of f is equal to derivative of f tilde times ds dx. So this part here is just chain rule. Okay. And the thing is, based on my formula for s, if I differentiate this with respect to x, x is being multiplied by a constant factor, 1 over h. So 1 over h is the derivative. So that's where this 1 over h factor comes from. So then I have a derivative of f tilde at s equals 0, because, look, from your association to this table here, if x is equal to x naught, then s is equal to 0. So 0 is what I plug in here. Now, f tilde is approximated by p2 tilde. It's polynomial interpolation. So I'll just replace it with p2 tilde prime, and then I have some error. Then I'll have to figure out what that is. Okay. Now what I do, and this is the last thing I did before I had to quit last time, I'm writing this also in Lagrange form. So, so p2 tilde is equal to my function values at minus 1, 0, and 1 times Lagrange polynomials. And because I'm taking a derivative and plugging in 0, I'm doing the same thing to my Lagrange polynomials. All right, so now to resume and finish this off. Okay, well, I'm going to go ahead and copy this. Whoa, stop it, stop it, stop it. Dang thing. Okay. So first, I'm going to replace all these f tilde values with f values, because I really want to express it in terms of that. So for instance, f tilde of -1 is the same as just plain old f at the corresponding x value, which is x naught minus h. And then s equals 0 corresponds to x equal to x naught, and then I'll take the tilde away there. And then finally, tilde f of 1 is the same as regular f at x naught plus h. So here I'm trying to get back to x land, if you will. So f tilde values become f values, s values become x values. Okay. Let me go ahead and write that down. So s goes to x, and then tilde f becomes f. So that's the change that's being made there. Okay. Now, what I need next, I need these Lagrange polynomials. And I need to take their derivatives and plug in 0. Now, I could work all that out on paper, but what I want to show you, for the sake of code that'll be written in homework 4, is how you would do this. How you do this in Matlab. Okay. So, all right. So to get coefficients in the center difference, my interpolation points are -1, 0, and 1, due to using x naught minus h, x naught plus h. Okay. So here's what I am going to do. So I'll go ahead and tell you what I'm going to do first, then I'll go ahead and do it. We need to form Lagrange polynomials for -1, 0, and 1. Then I'm going to take their derivatives. And then finally, substitute s equals 0, which corresponds to x equal x naught, because that's where I really want the derivative in x land. Okay. Now, so here's what I'll do. I'm going to call these polynomials. I have they're all degree 2, but indices -1, 0, and 1. So what I'm going to call these, first I'm going to make my s values. My s values are -1, 0, and 1. And then my first Lagrange polynomial, I'll call it LM1. And so the m means minus. So this is like L minus 1. And I'm going to cheat here and use MATLAB's polyfit function. So my s values are my interpolation points. Now, for a first Lagrange polynomial, I want it to equal 1 at this point, -1. I want it to equal 0 at the other 2 points. So those are my y values, 1, 0, 0. And I have 3 points, so this is degree 2. Okay. So, and we don't. The coefficients of this polynomial are immaterial. That's why I'm not even bothering to show it to you. We'll focus on the actual steps that are performed. Okay. So now I'm going to take the derivative. So I'm going to use a d for derivative. So I'll take polyder. Sorry. So the coefficients of LM1 are passed into polyder. This is a function that you'd actually end up writing for as part of homework 4. And it just uses a power rule, like it tosses out the constant coefficient, and then uses a power rule on all the rest of the coefficients to figure out the coefficients of a derivative. And then, finally, I'm going to plug in 0. And this, I do want to see what the result is. And I get minus 1/2. Okay. All right. Okay. Now, so that's my first coefficient. So C sub minus 1 is equal to minus 1/2. Okay. So now I just have to do this again for the other Lagrange polynomials. So I'll call this next one L0, because dealing with coefficient C0. And I need to change the y values only, because this polynomial, I want it to be equal to 1 at 0 and equal to 0 at the other points. So it would be 0, 1, 0. That's the only change I make. And then I go ahead and take its derivative. Using a power rule. That's what Polyder does. And then finally, I substitute in 0 into the derivative. And I get 0. So that's nice, because it means I don't actually have to use that function value after all. It's not going to be part of my approximation. Yeah. One polynomial left. So that's so in other words, C0 is equal to 0. And now I do L1. What should my y values be? If you look at what they were before, and considering how Lagrange polynomials work, 0, 0, 1. That's the last combination available. All right, so I have that, and then dl0 is derivative, and then I plug in 0 into that. Oh, tell me. Oh, I actually did multiple things wrong. I needed to take the derivative of L1. And I need to plug in 0 into the derivative, not the original. Okay. And I get 1/2. So C1 is equal to plus 1/2. So those are my three coefficients. So in general, use a loop. So S is multiples of H in points that are being used. And then your Y values, so you saw what the pattern was before. 1, 0, 0, 0, 1, 0, 0, 0, 1. These three together, if I were to stack them on top of each other, 1, 0, 0, 0, 1, 0, 0, 0, 1, what is that? What matrix is that? It's identity matrix. So your Y values are each row of identity matrix of n plus 1 by n plus 1 identity matrix. Let me make it a little bigger. So you do all this in a loop. So going from 0 to n, or 1 to n plus 1. The point is it runs n plus 1 times. You form Lagrange polynomials of degree n using each row of identity. Same s values, each one. Take the derivative, plug in 0, and then you have your coefficients. So now what I can do is substitute these coefficients into my form for my approximation. Okay. So I'll go ahead back to my document here and do that. Okay. Okay, so All right, so now these derivatives of Lagrange polynomials, these three, I'll just go ahead and replace with my coefficients that I just got. So that would be, so I'd have minus 1/2 for first one. And then this coefficient turned out to be 0. So that term's just gone. I'll just get rid of it. And then the other coefficient was plus 1/2. Okay. So now let's go ahead and clean this up. So I have, all right, so I'm going to have 2h in the denominator, and then my approximation will be f of x naught plus h minus f of x naught minus h, so that's the standard difference. So that's my approximation, plus error. Okay. All right, now getting the error is actually not very difficult based on a formula that's already worked out. So I'm going ahead and so I'm actually going to more easily see what's going on. I'm going to paste that from the book. Well, first, any questions about just getting the approximation? So all that happened here was using Lagrange interpolation at the points you're using, your x values that you're using, differentiate the Lagrange polynomials, plug in x equal x naught, bam, those are your coefficients. Or you can use interpolation points as your multiples of h, Lagrange interpolate those, plug in 0. Again, you get the coefficients. All right. Now, for the error, it just occurred to me this second that I also wanted to talk about integration today, so I'll be able to spend some time on that. Does there really need to be that much chatter down there? Oh, yeah, I kind of figured, but maybe if I yell, they'll hear me, but we'll see. Good point. Oh, well, the thing is, I don't accidentally disconnect Stennis. So, maybe. Well, I'll just put up with it because we have 23 minutes left. But I'll keep that in mind for next time. Okay. So for error, okay. All right, so the general form of the error is this. Well, f prime is equal to, here's your approximation, and then this is the error. So in this case, so I just want to focus on the error. So I'm going to get rid of the approximation part. Okay, so here's our error. Now in this case, n is equal to 2. We're using 3 points, second degree interpolation. So I'll just fill in n equal 2. So we have the third derivative, and then we have 3 factorial, and then I have I going from -1 to 1, but skipping 0. So really what I have is, x naught minus x naught minus h times x naught minus x naught plus h. Once you fill in all those details. But now I'm going to simplify. What can I simplify here? The x naughts will cancel. So let's get rid of those. So that happens in general. And then I have minus of minus h makes a plus. And then I have a minus h. So that becomes a minus h squared. So that's gone. I'll put the minus out front. And get rid of these parentheses. And, well, 3 factorial is 6, as I heard somebody whisper. So that's it. That's the error term that comes about just from plugging in all the information that you have. What are your x values? Just x naught minus h and x naught plus h. Once you simplify all of that, then there you have it. One of the explorations in homework 4 involves coming up with this kind of formula in general. If you do like certain examples, you can, based on the formulas that are already given in the text and their error formulas, you can get an idea of what the pattern would be. But see, the simplification that happens every time is you're always substituting in. So more generally, you have since xi is always equal to x naught plus ih, but then you simplify that as much as you can, and what do you get? You always get minus ih, where I is ranging from minus j to k and skipping I equals 0, because otherwise this whole thing would be 0. This relates to one of the explorations in section 8.1. How do you simplify this as much as you can? So I started the process, but this actually simplifies a whole lot more. And if you try this out with certain examples, like pick specific values of j and k, then you can get an idea of what the pattern is. Okay. So any questions about how this error formula came about? And thankfully, it's the same error formula that I came up with last time using Taylor expansion. Okay. All right. Now, the last broad topic of the semester, so what we're doing the rest of the way, is numerical integration. So the problem in this case is to approximate a definite integral of some function f over some given interval a, b. So f is given, a and b are given, and we have to approximate this integral. Now, so we recall how definition of definite integral. So the definite integral is equal to a limit as n goes to infinity of a. Does anyone remember the kind of sum that's used to define an integral? What's it called? Riemann sum. So we. Whoops! Come on. Okay. So then we evaluate f at various points, xi, and then multiply by spacing, delta x. And the spacing is always, in this case, for a straightforward Riemann sum, is always b minus a over n. And then the points that we use, that we plug into f, is always xi is equal to a plus I delta x. So here we're evaluating f at equally spaced points, and then we're now what does this integral mean? What's the interpretation of it? Anybody from Cal 2? Geometric meaning of the integral? Geometric meaning of the definite integral? Area under a curve. So, now those of you who are Cal 2 instructors subjecting you to this, what did they have you do when approximating these areas? Like what kind of shapes did they have you use? Rectangles. By the way, one of my colleagues in this department, they were teaching one of the classes for I think elementary ed majors, so they'd be teaching math for elementary students. They did not know what the formula for the area of a rectangle is. So, unless you want me to be completely disillusioned at this moment, you will tell me what it is. Seriously. Did you say width times width? I'm retiring. Width times height. Thank you. Saved the day. Okay. Yeah, delta x is a width. F of xi is a height. Okay. Now, the thing is, so a simple approximation is you choose. Whoa, I want this to be outside the equation. Okay. So we could go ahead and choose some n, and that's the number of rectangles. And then what you have is that my integral is now approximately equal to, I'm no longer taking a limit as n goes to infinity. I have a fixed n, and then the rest of it stays the same. So now I'm using a certain number of rectangles. And as you know, as you would imagine, the larger n is, the more rectangles I use, the more accurate my approximation will be. Now, can anyone tell me, if they remember from Cal 2, there were different kinds of rectangles, or really there were different ways of getting the heights. Does anyone remember what those were?
Like the right side, left side.
Yes. Left endpoints, right endpoints. What was the other one? Midpoints. Midpoints is actually far more accurate. Left endpoints and right endpoints. This is right endpoints right here, just an example. If I change this to I minus 1, it's left endpoint. If I make this I plus a half, or no, I minus a half, it's midpoints. Left and right endpoints are such horrible approximations, we won't even talk about them. Midpoint, that's something more reasonable. But generally, this is a very bad approximation. So we need to be more flexible. So what we're going to do instead is we use what's called a Quadrature Rule. So the idea is, so the integral is equal to a sum of this form, and a Riemann sum can be of this form, but we're going to have different, but we're going to make some changes to it. Okay. Now for some terminology here, the xi's are called nodes, and the w's, y's, are called weights. So the idea is, now you can still think of these as playing a role of widths and f of xi being height. It's still rectangles. And in fact, that kind of leads to the name Quadrature Rule. Quad for quadrilateral. It could be rectangles or even trapezoids. We will see trapezoids later on. In your Cal 2 class, depending on your instructor's preferences, they may have covered the trapezoidal rule for approximating integrals, or Simpson's rule. We are going to revisit those, but also some better techniques. Okay. So every technique we will see for approximating integrals will have this form. They'll evaluate f at various points, multiply those values by certain weights, and choose the nodes and weights to get the integral as accurately as possible. So the goal is we want to maximize accuracy, but minimize, minimize n, because for efficiency's sake, because we want to evaluate f at as few points as possible. We don't want to. We can always get as much accuracy as we wanted if we were content with evaluating f at like 1 million points, but that's a waste of computing resources when we can get away with far less than that. Okay, so that's one key criteria that guides what we do in the rest of this chapter. Now, the quadrature rules that we will use are based on this form. Interpolatory quadrature rule is a type of quadrature rule where the weights are determined by approximating f by a polynomial of degree n-1. So the idea is the interpolation points are the nodes. So we have if we're going to approximate integral of f by, because we have a polynomial that agrees with f at the nodes, and then we're going to integrate the polynomial exactly because polynomials are so easy to integrate. So what we do is the integral, the exact integral, is approximated by the exact integral of a interpolating polynomial of degree n-1. But how can we write that interpolating polynomial? Just like with derivatives, Lagrange form. So we have the f values as a coefficients. Well, I'm going to have a sum here. And then I have my Lagrange polynomials of degree n-1. Okay. Now, what can I do with integrals? I can pull sums out of them. I can pull constants out of them. F of xi is a constant. It's not a function of x. So I'm going to go ahead and do those simplifications. So now I'll have f of xi pulled out. The Lagrange polynomial I need to leave in there. Okay. Now, if we go ahead and compare this approximation of the integral to the general quadrature rule up above, they both have a summation, exact same summation. They both have f of xi. What's left? We have the weights up here. We have the integrals of Lagrange polynomials down here. So what does that mean? We have a formula for weights. So any interpolatory quadrature rule has its weights predetermined. So once you've chosen what nodes you're going to use, and that is a science in itself, bless you, then once the nodes are chosen, these are the weights. They're the integrals of Lagrange polynomials. Now, I can draw a parallel to what happened in differentiation. The coefficients are the derivatives. Whoops, that's weird. Oh, I see what happened. Okay. The coefficients for derivatives that I was doing earlier today are but derivatives of your Lagrange polynomials evaluated at x naught. For integration, the coefficients are the integrals of your Lagrange polynomials. The point is, in both derivatives and integrals, what you're doing is you're expressing what it is you want to compute, derivative or integral, as a linear combination of function values. The coefficients are obtained by solving the problem you want to solve, derivative at x naught, definite integral over ab. Whichever problem you're trying to solve, you solve that problem on the Lagrange polynomials. And there's your numerical differentiation or integration scheme. It's exactly the same idea underpinning both. Okay. Now, so the thing is, now that we've seen what an interpolatory quadrature rule is, I can answer this question. Why are Riemann sums so bad? And the reason why is they use a piecewise constant approximation of f of x, because what you're doing is you have rectangles. The height of each rectangle is determined by the value of f at each point. If f cannot be well approximated by that kind of piecewise constant function, then your approximate area is going to be off. By contrast, interpolatory rules, they approximate your integrand by polynomials of degree n-1. Now, for the most part, we're generally interested in evaluating integrals of continuous functions. So if you're going to do that, it makes sense to approximate f by a function that is itself continuous. And that's what interpolatory quadrature rules are based on. So, in fact, actually, my earlier comment has there's one caveat to that. One exception. Well, actually, never mind that. It's always the case if you use rectangles. If trapezoids are used instead, then that has the effect of approximating f of x by a piecewise linear function. It's continuous, so it's a better approximation. And we'll talk more about the trapezoidal rule next time, like on Tuesday. But so that's one approximation to look at. Also, like Simpson's rule, it uses a piecewise quadratic approximation, so that accounts for any curvature in your function's graph. So it's an even better approximation. Now, what we're going to see during this chapter are many different methods that all have this form. We pick some nodes, we choose some weights. So it might seem strange to go to so much trouble, especially if we're using computers that can perform a zillion operations a second. In fact, I should probably use that in our marketing literature, literally a zillion, whatever a zillion is. Why do we go to much trouble to pick the right nodes and weights? And so the reason why, but I'll give it these last 3 minutes. Okay. And I'll see more of this. You'll see more of this later. But my favorite example is the integral from 0 to 1 of e to the minus x squared dx. An integral that is absolutely impossible to evaluate using techniques from Cal 2. So using trapezoids, which is normally a good technique, for certain functions it's the best technique. we need about 2,500 trapezoids to get 8 digits of accuracy. So in other words, n, the number of points we need, about 2,500, roughly. Okay. Now, for comparison, Simpson's rule. That's piecewise quadratic functions. And this is a bell curve, so you want to use an approximation that has some curvature to it. Need n is roughly, I think like 33. So huge improvement. Almost 100 times fewer points. One of the last topics we'll cover, Gauss Quadrature. Need 5 points. So you play your cards right, you're smart about it, you can develop a technique for solving your problem that cuts the computational effort by these kinds of factors, like hundreds or thousands of times faster. That changes scientists and engineers, researchers' workdays. If you present them a method that gets a job done for them hundreds or thousands of times faster than before. That's what I've done in my research. My methods are that much faster. Again, literally hundreds of times or thousands of times faster than they were when they started. And so from understanding what causes methods to slow down, what causes less accuracy, less efficiency, we can always find ways to improve them when that might have seemed outside the realm of possibility before. So that's what we're going to see by the end of a semester, are a wide variety of approaches. Also, no one approach is the best for all problems. There are certain integrals for which this lousy method, trapezoidal rule, is still actually the best. So we have to be aware of all of these approaches. You never know which one will suit a particular problem you're dealing with. Okay, so we'll continue with integration on Tuesday. Well, for the rest of the semester, really. So.